This video will cover a solution guide to problem 62 from chapter 3. A rock is thrown with a velocity v0 at an angle of alpha naught from the horizontal from the roof of a building of height h. Ignore air resistance. Calculate the speed of the rock just before it strikes the ground and show that the speed is independent of the angle. We have quite a bit of information explicitly and implicitly given to us in this problem, so let's start by figuring out what we have to work with. In the x direction, we can set the rock's initial position to be 0. With the velocity vector and angle I've drawn, we can determine the x component of the velocity to be the magnitude of the initial velocity times the cosine of alpha, and, neglecting air resistance, makes the acceleration in the x direction equal to 0. In the y direction, we have the rock's initial and final positions. We can also define the initial y component of the velocity as the magnitude of the initial velocity times the sine of alpha. We also know that an object in freefall has an acceleration equal to g. We don't have the time it takes for the rock to reach the bottom, and we don't know the horizontal distance that it covers, but that's okay. We don't need them. If the rock is thrown upward, it follows the dotted path shown in the picture. At its peak, the vertical velocity is 0 and then starts moving back down towards the earth. At the point where the vertical displacement is equal to 0, the magnitude of the velocity is equal to the initial velocity the rock was launched from. If this is not immediately obvious at this point, that's fine. We can prove it. The rock is only being acted on by gravity, so we can use a constant acceleration formula to find its velocity when it reaches its initial height after being launched. If we use this equation, we can plug in minus g for the acceleration, and since the total displacement at this point is 0, delta y is equal to 0. Simplifying, we can see that the square of the y component of the velocity at this point is equal to the square of the y component of the velocity initially. From the sketch, we can see that the y component of the velocity would be equal but opposite to the initial y component of the velocity. We can now treat this problem as though the rock were being launched downward at minus v instead of upwards. Using the same equation we used above, we can calculate the final y component of the velocity. In this situation, delta y is no longer 0. Instead, it is falling a distance h, so we will substitute in minus h for delta y and minus g for the acceleration and solve for the velocity in the y direction. We will keep it in its square form since we will need it that way in a second. To find the magnitude of the total final velocity, we simply need to take the square root of the sum of the squares of the two components. As was mentioned at the beginning of the problem, there is no acceleration in the x direction, so the final velocity in the x direction is equal to the initial velocity in the x direction. Subbing this and the expression we got for vy final squared above into our definition for the final velocity, we get this expression here. Factoring out a v0 squared, we end up with a cosine of alpha squared plus sine of alpha squared. Recalling some trig identities, we know that this sum is equal to 1, so our expression for the final velocity simplifies to the square root of the sum of the initial velocity squared plus 2gh. This expression is completely independent of the angle we initially launched the rock from. In other words, we could have shot the rock off the building horizontally, angled down, or really just however you felt like it. The horizontal distance would obviously change, but the speed at which it strikes the ground would always be equal to the expression we just derived.